So in this last lecture, we are going to continue looking at topos theory, and I'm mostly following this book. It's a very nicely written book with lots of examples and motivation. Sheaves in Geometry and Logic by Macklin and Mordyke. And I mentioned last time that topos theory is like an elephant. It has got multiple different interpretations. It can be thought of as a generalized space, as a generalized universe of sets, or generalized or as a classifying object as well. So Grothendieck gave this definition of a Grothendieck topos, and that will be the end goal of our today's class. But what we saw last time was a slightly more general class of toposes, and that was Lavere and Tierney's definition of an elementary topos. Okay, so we saw the definition. Let me remind you. So is an elementary topos if it is a Cartesian closed category with a subobject classifier. So this subobject classifier is something very important. It's the universal subobject, universal monomorphism, such that every monomorphism is a pullback of this universal monomorphism in a unique way. Yeah, there isn't anything different happening, and therefore the sub E is functor. This functor is representable, I mean co-representable to be proper, and the power objects also exist, and they satisfy all the nice properties, and we saw a bunch of properties of elementary toposes. So one thing I like, before I go on to examples, one thing I should add here is that a morphism between elementary toposes is called a logical morphism. Logical morphism. Now, logical morphism is something very simple. It should preserve everything that is part of the definition. Yeah, so i.e. a structure preserving map. So what should it preserve, tell me? It should preserve finite limits, then it should preserve exponentials, and it should preserve subobject classifier. Yeah, so those are the things it should preserve, right? So that's just a simple thing. It's a logical morphism, whereas between Grothendieck toposes, the morphisms are called geometric morphisms, and geometric morphisms are supposed to be pairs of adjoint functors where the left adjoint is left exact. Yeah, so there are different purposes. Logical morphism, because here we are really talking about logic. Yeah, we are trying to generalize the universe of sets. So elementary toposes are such generalized universes of sets. So now we can start looking at some examples. Even before we define a Grothendieck topos, let me tell you that those are all co-complete categories. Complete and co-complete categories. Yeah, so therefore they are very nice. So out of these examples of elementary toposes, some will obviously be examples of Grothendieck toposes. Yeah, you should be able to figure them out. So for let's look at some examples. First one, can you guess what the first one is? The category of sets. Very good. Category of sets is Cartesian closed and has a subobject classifier. What is the subobject classifier here? We already saw that. Yeah, the omega is 0, 1 and true map is, and true from 1 to omega is the only element 0. Yeah, I mean this is equal to 0 and this is equal to 0, 1. So the only element 0 is getting mapped to 0 itself. Okay, so along similar lines, because we never asked for any existence of infinite limits, so the category of finite sets is also an elementary topos. For exactly the same reason, because the subobject classifier is still within the category of finite sets. And exponentials, yeah, that is also an important property. Exponentials of finite sets are again finite. Finite to the finite is finite. So that's why it works. More generally, you can talk about any, what kind of cardinal, any regular cardinal, you can talk about, yeah, so all sets of cardinality less equal a particular regular cardinal. That will also work. Okay, so let's not worry about that. Then another thing that you can do is you can define sets to the power n, where n is a discrete n element set. This is also an elementary topos. Can you tell me why? What will be the subobject classifier?
It's the empty set, sorry,
0, 0, 0, 0 n times. Yes. So the what is omega there?
It takes all those zeros to 0.
Omega is 0, 1 to the power n. Yeah, obviously, it's just component wise. Finite limits are component wise, and omega is this. How many truth values are there here? 2 to the power n. Yeah, in total there are 2 to the power n truth values. So it's a Boolean algebra, finite Boolean algebra with 2 to the power n. In fact, you can recover any Boolean algebra as a subobject. Any Ising algebra as a subobject. I will talk about it. And true is obvious, yeah. True is the obvious map. But you don't just stop here. You can go ahead in the similar way. You can also describe sets to the power arrow. Yeah, these examples I will invite you to verify these things yourself. Arrow is, you remember the arrow the category of arrows? The arrows in sets, the functions are the objects and the commutative squares are morphisms. So in similar spirit, you can also do sets to the power n, natural numbers. In fact, why stop here, right? We can actually say that C of sets for a small category C, small or skeletally small, small category C is the pre-sheaf category. So we defined pre-sheaf as just a contravariant functor on a small category. So the pre-sheaf category is an elementary topos. Okay, we have to verify a few things here. Yes.
The category of small categories also a topos?
The category of small categories is not a topos. No.
What
It won't have a subobject classifier for sure. Okay, I'm going to like expand upon this particular example, C of sets, in detail. But before that, let me give you some other examples. So the category of simplicious sets, that is an elementary topos in particular. Why? Because it is, no, it's not n. It's delta of sets. where delta is the simplex category, yeah, with finite sets and finite linear orders and monotone maps between them. So this is an example. Then seventh example, which you shouldn't find surprising at all, that the category Bm of monoid acts for a fixed monoid M. Monoid acts, what is the category actually? It is the functor category. Yeah, I mean, this is precisely the category M sets. And since M can be written as M op, so this is an example of a pre-Schiff category. Then Bg of G sets for a fixed group G. Yeah, because this is same as G sets. So nothing is changing. But more importantly, the category Bg of continuous G sets for a fixed topological group G. That is also an example of an elementary topos. So, what is the meaning of continuous G sets? That the action G cross X to X, that map is continuous with respect to the given topology on G and discrete topology on X. The operation on G, the multiplication operation, the inverse operation, they are automatically continuous as part of the definition, but on X you substitute, you equip it with discrete topology. That's the only thing you can do. So now observe this list. Out of this list, all but the second example, they are also Grothendieck toposes. Okay, because they are all co-complete. I haven't defined a Grothendieck topos, but I am already telling you that this is true. And one non-example I can give you, like category of abelian groups is not an elementary topos. Why is that the case? Because if it were to have a subobject classifier, because a subobject classifier will be what? It has to be a map from 1 to some omega. What is 1? Is a map 0 to omega. Well, what kind of map can it be? 0 map. So now you want omega to satisfy the universal property. What universal property? That for any b dash subgroup of this, then there should exist a map such that this 0 map makes this diagram a pullback. What will happen here? That composition is 0, so this composition will have to be 0. So B to omega map has to map B prime to 0, right? So therefore, the kernel of this map, like whatever is this is M, this is chi M. So kernel of chi M, yeah, this one has to factor through this. So what are you expecting out of this? Like every single kernel Do you understand like what's happening? It's demanding too much. This thing is demanding too much. Like the object, if it exists, such an omega, if it exists, then it has to contain the kernel of every single map to that as inside it. Yeah, so it has to be a massive object which will not exist, obviously. So therefore, this is not an elementary topos, and for the same reason, you can check that the category of small categories is also not an elementary topos. So I'm going to expand on number 5 now. Okay, so number 5 is the essential example here. So the pre-shift topos. Since I won't have enough time to talk about the sheaf topos enough, okay, I think I should add one more thing. Yeah, I forgot to mention that. The 10th example I should add as the category of sheaves on a topological space. This is an example, yes.
So is the category of toposes a topos?
No. No. In fact, there is a result in like toposes have a sense of direction. I don't remember the exact result, but I think if yeah, I remember the result. If E is a topos and E op is also a topos, then E has to be 0. There's nothing else happening. Like 0 category, empty category. Yeah, there is nothing else possible. The subobject classifier gives it a sense of direction. It's always increasing. In the category of sets, we have ordinals. Yeah, they are ever growing and growing and growing. So same idea over there. Okay, so now our main point is to understand the category of pre-sheaves. Well, do you understand why this category is Cartesian? Why does it have finite limits?
Because
Sets is Cartesian. Yes, so therefore C of sets is Cartesian. Yeah, the forgetful functor. No, I mean it's pointwise. In the functor category, every limit and co-limit is computed pointwise. So therefore it works. Now, if like, okay, let me also give a notation C hat. C hat is the notation for C of sets. So if C hat has a subobject classifier omega, then, well, what should it satisfy? We will only look at the representable functors first. Yeah, then sub C hat of YC. YC, where Y is the Yoneda embedding, C is any object of C, will have to be isomorphic to what? In the category C hat, if such a subobject classifier exists, then you simply have to substitute this. Yeah, the sub C hat is a co-representable functor, so therefore it has to satisfy this identity. But now what is this? What are the morphisms in C hat? They are natural transformations. So natural transformations from a representable or a co-representable to another thing, what will it be? Yes. So then the pre-sheaf omega has to be evaluated at C. So let's make this the definition of omega C. Then it should satisfy, then it, yeah, then this will happen. So choose So choose omega c to be equal to the subfunctors of the representable functor. Okay, let me quickly remind you, what is the meaning of a subfunctor? Like if Q is a subfunctor of Yc, then there is a monomorphism. Then for each D in objects of C, what will happen? Q of D is a subset of Yc at D, which is by definition, what is Yc at D?
C of C comma D.
Yes, C of C comma D. So it is just some collection of morphisms from C to D. No, shouldn't it be D to C? C to C offsets. Yeah, Yc is the representable functor. So it has to be the contravariant functor. So CDC. So QD is a subfunctor of this. Okay. You understand this? So omega c is the collection of Q such that Q is a subfunctor of Yc. Okay, C blank C. Okay. Now, if you look at this, then you are basically talking about a subfunctor, like talking about a subfunctor of Yc is just making a choice of morphisms with codomain C. C is fixed here, yeah, D will vary. So we have to talk about some morphisms with codomain C. And moreover, they need to have some properties. Yeah, because this is a subfunctor and not just a subset. QD is not just a subset. If there is a morphism from D to E, then there should be a morphism from QE to QD, which takes it in the reverse direction. Right? So if I have some morphism from D to E, then which way will it go? If I have a morphism from E to C, then I will have a morphism from D to C. That's the natural way it works. So for this reason, like for this diagram to commute, what we need is a collection of morphisms which is closed under precompositions. Okay. So in other words, the right ideal notion is relevant here. So now let me define this other notion. So say that a set S of arrows with codomain C is a sieve on C if it is a right ideal, if it is closed under precomposition with arbitrary elements. Okay, what I am asking is this. So if i.e. if f belongs to S, then f composed with G belongs to S for any G such that f composed with G is defined. Okay, so this is a sieve. So let me try to draw something like, and hopefully you will understand why it is called a sieve. So there are certain morphisms which you allow. Yeah, and then many things are coming in. And maybe there are some certain arrows through which you do not allow stuff. So it's the arrows with codomain C that gives you a sieve. Only those things can pass through and the other things cannot pass through. So it is a collection of arrows. The domains of such arrows don't matter. It is simply a collection of arrows which is closed under a precomposition, or it is a right ideal. Yeah, so this is the right ideal condition. So you can say that a sieve is a right ideal. Dually, a left ideal would be called a co-sieve. Yeah. So in French, the word sieve is written as crible. In French. So this is a terminology coming from agriculture, as I said yesterday. Okay, so right now we have got two different notions. One is a subfunctor, another one is a sieve. And those are actually the same. Okay, so let me write what I want to say. So given a sieve S, yeah, define define Q of A to be equal to all those morphisms in S such that domain of F is equal to A. So that Q is a subfunctor of YC. Okay, so this is one way, and in the other way, in the other direction, given a subfunctor Q of YC, define S to be the collection of all those arrows F such that F is an arrow with codomain C, and F belongs to Q of its domain. This will give me a sieve back. So that S is a sieve. This correspondence is very important. So thanks to this correspondence, we can redefine omega in the pre-sheaf category, the subobject classifier in the pre-sheaf category, as the collection of sieves on C. You understand? So therefore, omega C can be thought of as the set of sieves on C. Okay, once we define this notion of, like, this is definitely going to be a set. Do you agree with that? Because we start with a small category. And the collection of sieves, yeah, I mean, we have to talk more about it. It's not the end of the story because we have only defined the object omega so far. We haven't defined the true map. So try to give me some example of a sieve. The most obvious one that comes to your mind.
All maps with code.
All maps with codomain. So that will correspond to which subfunctor? YC is a subfunctor of YC, right? So let's define that now. So max of C, yeah, which is equal to collection of all arrows with codomain C is an element of omega of C. The true map, true map, like, where is it from? True is from 1 to omega, but is it's a map in the pre-sheaf category. So you will have to specify it at an object has components true sub C from 1 at C, 1 evaluated at C, to, like, this has to be a monomorphism again, to omega sub omega of C. What is 1 of C? It is a singleton. Terminal object is pointwise terminal, right? So it's a singleton. So the only element here will have to be mapped to the only sieve whose existence we always know, namely the maximal sieve.
We also know like the smallest sieve that there is the collection of no arrows.
The collection of no arrows, will that be a sieve?
It is closed.
Okay, so that will be our false. Yeah, so that will be the false map. And the truth values, now you can see, the truth values of this, in this omega, they correspond to sieves, like collections of sieves at every object. But there has to be a network. And because this is a functor, what does that mean? So given F from B to C in C and S in omega of C, like S is a sieve on C, F star of S defined as all those arrows such that codomain of G is B and F composed with G is in S. So this is an element in omega of B. So given an arrow, I have arrow in the category C, I have a map in the opposite direction. I have a map from omega C to omega B. So this defines omega as a functor. Yeah. So this assignment makes omega a pre-sheaf, and together with the true map above, it is a subobject classifier. Okay, so now I have to prove to you why it is a subobject classifier. So given, like I'm telling you the proof, given Q as a subobject of P, yeah, define phi C. I mean, yeah, okay. I'm not giving it a name, but define phi C from PC to omega C. So here is the diagram that we are trying to prove, that it's 1 and this is omega, this is our true map, and this is the monomorphism that I am using. I will never use it. So I need to find a map from P to omega corresponding to this M, and I am going to call it phi. So I have to define phi C from PC to omega C for each C. So what will I do? I will take an element, it has to be a function, right? So PC is a set. So I will take an element and then I will map it to all those morphisms F from A to C such that PF of X, it belongs to Q of A. Okay, so there are many categories at work. So P is a presheaf. So it is a contravariant functor. So PF of X is going to be an element in P of A ordinarily. Yeah, because P is contravariant. F is a morphism from A to C. So PF goes from PC to PA. But what we are asking is that PF of X is an element of QA. The collection of all such morphisms, you can show it to be a sieve. So this will be a sieve and therefore it is an element in omega C. For each such element, we have such a map. Yeah, so this is a sieve. And this particular assignment, like this is the characteristic function. I could have called it, let me call it just chi.
Omega of C is a set.
Huh?
Omega of C is a set.
Omega of C is the collection of all sieves.
On C.
On C, yes. And I am associating to an individual element X in PC a sieve. Right, so this is the characteristic function of the map M. The other way is clear. Yeah, I mean, you can verify the details of this bijection. The other side is always clear that given any map, pullback of a mono is mono. So you'll always get a subobject. You have to verify that this association is bijection. Okay, so therefore you do get a subobject classifier subject to your verifications. Yeah, the challenging part here is to get your head around which category you are working with.
So the subobject classifier will be the collection of all sieves.
Subobject classifier is the functor which assigns to each object the object of the base category, the collection of all sieves on that object. Yeah, so this is the main defining property. Okay, any questions so far? Okay, I will also give you one more thing. So the next part is that C hat is Cartesian closed. So without Yoneda, this was not possible. Yeah, I mean, let me go back to this. If at all it has a subobject classifier, then what it should be was already given, like already presented to us thanks to Yoneda lemma. And in a similar spirit, if at all this category has exponentials, then that will be presented to us on a platter by using Yoneda lemma and appropriate adjunctions. So C hat is Cartesian closed. So given P and Q in C hat, objects of C hat, if Q to the power P is defined, then What will be q to the power p of c? Well, it will have to be isomorphic to, this is a functor, yeah, q to the power p will again be an element in c hat. So thanks to Yoneda, it will be the set of natural transformations from yc to q to the power p. This is Yoneda. And well, what is this? Thanks to the adjunction, product and exponential adjunction, that will be yc cross p to q, which is defined, yeah, the set of natural transformations from this product pre-sheaf to q is defined. So define, so use this to define q to the power p. Okay, that's how you define exponentials. It looks complicated, but these things are really important. Yeah, exponentials and subobject classifiers. Yeah, so Yoneda lemma makes our job very easy.
Yeah, it's like, I mean, whenever we're trying to define something, it's always looking in the home set and then looking
Yes,
in,
you have to,
transfer.
yeah, you have to do it at the Yoneda functor. Yeah, then everything will work nicely. And this particular exponential will satisfy all the nice properties that you want it to. When I saw this for the first time, I was really excited because you don't really know lots of definitions of exponentials beyond numbers. Yeah, in these, there are so many examples of categories in which you can define, do exponential arithmetic properly.
Can we express the exponential of Lie groups
Exponential of Lie groups?
using like something like this?
I don't have any idea. But I guess like not in Topos theoretic language. Or maybe you can do it in synthetic differential geometry. Yeah, perhaps you should check that. Lie groups have to do with differential geometry, so synthetic differential geometry is the natural choice. Yeah, I'm sure it has been done then. Because Lie groups are what? They are the group objects in the category of differentiable manifolds. And if you can define differentiable manifolds like using synthetic differential geometry, then you look at the group objects. You interpret the theory of groups in that category. So
Then we also have to look at the tangent spaces.
I'm sure all those things are done. There is a third volume of sketches of an elephant where there is an entire section on. So part E or F of elephant is about synthetic differential geometry. And it is available, at least an online version I have seen. Yeah, originally it was just first 2 volumes, but after about 15 years, 15 to 20 years, he released a third volume. Okay, so there are some more properties of the category of pre-sheaves which are worth mentioning. Yeah, and this is also very interesting. Every pre-sheaf, I mean, these are all the tools used in Topos series. So every pre-sheaf can be expressed as a canonical colimit of the representables. Canonical colimit, as in the shape of this category, the shape category can be determined by the given category, the given functor, given pre-sheaf. So given, now I will show you how to do that. So you will still have to fill up the details later. Given P in C hat, a pre-sheaf, define its category of elements denoted integral P over C. Yeah, as follows. So the objects are pairs P comma X. Sorry, objects are pairs C comma X. For C is an object of C and X an element in PC. And what will be the morphisms? Morphisms from Cx to C prime X prime are morphisms f from C to C prime such that Pf x prime is equal to x. It has to go in the reverse direction because it's a contravariant functor. Okay, so that association is inverted. Then clearly there is a projection functor from the category of elements, let me call it pi p, from category of elements to C. What it does is it takes C comma X and maps it to C. Okay, so this projection functor, what is the use of this?
To construct its adjoint.
Yes. Okay, I'm not going to go into the details, but like it can be verified that
The adjoint will be the home functor, home CP.
the co-limit, that P is isomorphic to the co-limit of this diagram. Like the diagram is this, pi p to C and then y to C hat. So the category, shape category is the category of elements, and then you go down to the base category and then you embed it using Yoneda embedding. So P is isomorphic to this. The proof proceeds via some Khan extensions essentially, but I'm not going to give you the details. The point is that every presheaf can be expressed as a canonical co-limit of representables. Yeah, so presheaf category also has this nice property which is heavily used in the proofs in Topos theory. Okay. Any questions so far? So far what I have told you is that, you already know that the category of presheaves is an example of an elementary topos because omega exists. It also has exponentials. But I want to reach the definition of a Grothendieck topos starting from this list. And I want to add many more examples. And the example that I want to focus on over here is the last one, number 10. That the category of sheaves for a topological space X. Now, not every presheaf turns out to be a sheaf. It is a subcategory. So this, you remember that sheaves on X is a full subcategory of the category of presheaves on OX. Yeah, OX op. This is a subcategory of OX op where OX is the set of open sets, okay. So there is an equalizer diagram which describes sheaves amongst pre-sheaves. But before I do that, I will have to first generalize the concept of an open covering. There we had an open covering. If you remember what we said, you take an open set U, and whenever you have an open cover, then with respect to that open cover, so maybe I should write it down, yeah. So recall that F in OX op sets is a sheaf if the sheaf condition holds. Yeah, what is the sheaf condition? It says that if for any open cover UI of U in OX, if we have local sections FIs which are compatible with each other, like Fi restricted to UI intersection Uj is equal to Fj restricted to UI intersection Uj, then there exists a unique F like a section on U such that its restriction is restriction to each UI is Fi. So that can be written as this. Well, let me write it. So you can take product of FUI, I from I, and then there are two different maps. I'm calling them P and Q, and there is a massive product here over Ij in I cross I, and this is F of UI intersection Uj. And Fu to this is an equalizer. If this is an equalizer diagram, so what is the map from here to here? If you are given some elements xi, I'm not using the notation of functions anymore, but this is xi I in I. Where will it map under P? Yes, xi restricted to UI intersection Uj and Ij in I, and under Q it will map to xj restricted to UI intersection Uj, Ij in I. And what is the map here? A single element x will go to, yes, x restricted to UI. I mean, the restriction is actually given by the restriction maps. I mean, technically speaking, what I should be writing here is rho UIU of x. Yeah, but I'm not doing that because you understand it better as functions, local sections. So if this is an equalizer diagram, yeah, this equalizer diagram is really crucial because we are going to show that every Grothendieck topos, yeah, which is going to be a localization, and localization means it's an adjunction, it's a reflection where the left adjoint preserves finite limits, and that happens thanks to this equalizer condition. Okay, so that's the main idea over here. Now we have to generalize the concept of an open cover to an arbitrary base category C. Yeah, we only know it for OX op. So the open cover means that the union of UIs is equal to U. Now we have to talk about what is the meaning of covering an arbitrary object. Well, for that we have to describe a Grothendieck topology. This is Grothendieck topology or Grothendieck covering, which changed, this particular concept changed the face of algebraic geometry forever. After the introduction of sheaves and Grothendieck topologies, then the algebraic geometry is now known as modern algebraic geometry. It uses this abstract, heavy looking machinery, but once you get used to it, it's pretty straightforward. Okay, so given, I'm going to do it only with a small category, but you can do it with a skeletally small category as well. Given a small category C, a Grothendieck topology J on C is an assignment to each object C of C, a sieve, a collection of sieves a collection JC of sieves on C satisfying the following properties. Okay, so here, like before I write down the properties, do you understand that JC is a subset of omega C? Omega C is the collection of all sieves. I am going to declare only certain sieves as covering sieves. Okay, not all sieves will be covering, only certain sieves will be covering, and whatever is the notion of covering, they have to satisfy some coherence conditions and some non-emptiness conditions. So the properties are pretty straightforward. The first two properties are pretty straightforward. First one is that max of C belongs to JC for each C in C. So JC, like the maximal sieve is always a covering sieve. Well, you should hope so, right? And this is an analog of the condition in topology, in the definition of topology, that the whole space is always open. You don't, like Grothendieck topology, in my opinion, this is just plainly my observation, it's not written in any book, that Grothendieck topology is very much similar to the ordinary definition of a topology, except that it doesn't necessarily ask you to have empty set as open. So the points of this topological space, like it's not just one topological space, but you think of all arrows coming to C as your points. Then certain subsets of them are open. Other subsets are not open. Right? The entire collection of arrows coming to C is open. Then you can eventually prove from this definition. The definition looks abstract, but you can eventually prove that if there are two open covers, then their intersection is also an open cover, and so on and so forth. Like if you are given any open cover, then its superset will also be an open cover. So it's also like the definition of a filter. So in an appropriate poset, it's a filter. And now it's not just happening at object C, it's happening everywhere. And there are such different topological spaces connected like via morphisms, and the morphisms themselves are the points. So it's a very beautiful network of topologicals, like the weak definition of topological spaces. So first one is max. The second one is that, well, if S belongs to JC and F is a morphism, F from D to C is any morphism in C, then F star S belongs to J of D. This is like a continuous map. Every pullback of a sieve is like a continuous map. And it's going in the reverse direction, obviously. Yeah, so just like continuous map will require that inverse image of open is open. So this is like that condition. And third condition, well, the first one is called like maximality. The second one is called pullback axiom, maximal axiom, pullback axiom. And the third one is called transitivity axiom. So max, maximal, then pullback, stability under pullbacks, and this is transitivity. Now transitivity is a bit hard to understand. So if S belongs to JC and R belongs to omega C, satisfies, okay, so the following. What is the following condition? That H star of R belongs to J of domain of H for all H in C, in S. So if there is a sieve that I want to test whether it is covering or not, then one good test is that I choose some covering sieve and I show that the pullback of my R under arrows in that covering sieve are always covering. Pullbacks under all arrows of a covering sieve are covering, yeah, then R itself is a covering sieve. This is a complicated axiom, but it's also very useful. Okay. Well, this is the definition of a Grothendieck topology, but you won't really understand much unless I give you some examples. So let's look at some examples. So, okay, the first one is the trivial topology. Well, these are all closure axioms. Second and third are closure axioms. The first one is the real deal. Yeah, first one is it says that something is non-empty. So trivial topology means that JC is equal to singleton maxi. You don't choose any other sieve as covering sieve for each C. The localization with respect to this particular trivial topology will be the presheaf category itself. The localization of the presheaf category will be presheaf category. Right, so it's a trivial localization. That's why it's called trivial topology. Well, maybe I should add one more piece of, yeah, a site, a Grothendieck site is the pair Cj. So I'm describing some sites for you. So trivial topology, can you check can you verify that pullback of the maximal sieve is again the maximal sieve? Yeah. So it's trivial to verify that the trivial topology is indeed a topology. Okay. The second one, and here I will have lot of things to do. It's called I think it's called a subregular or something, but I'm just going to call it the regular topology. Yeah, regular topology. Regular topology on OX. On OX. So what does it do? It's the open cover topology. Yeah, this is the open cover topology. Now what you need to verify here is that the whole thing, like the collection of all subsets of a fixed open set U, that is obviously its union is going to be U itself. Then whenever you have an open cover, its pullback under any arrow is again going to be an open cover, because F inverse behaves well with respect to unions, right? Then the third condition can also be verified. Now OX, if you think about it, then OX has very limited connection with X. X is a topological space, but OX is just a lattice which has some extra properties. Okay, so we should try to generalize this. So more generally, okay, so this is a define a frame to be a lattice L finite meets arbitrary joins, and I think you'd yes, to be a lattice with finite meets arbitrary joins, and I mean the usual properties for meets and joins, and in addition the infinitary distributive law. What is the infinitary distributive law? That given any element A, if I am taking arbitrary join, then that is equal to the arbitrary join of A mid Bi. Okay, so this is the infinitary distributive law. So these are complete lattices, obviously. Even if I did not write 0 and 1, those are present. It is a bounded lattice thanks to arbitrary unions. So arbitrary union of nothing is 0, and arbitrary union of everything is the top element. So those are present. So a frame is a lattice like this.
And by trivially frame is that open cover topology.
Not open cover topology, but the open sets. Yes. So examples. Yes. So okay, let me define. There is a category FRM of frames and frame homomorphisms. So what are frame homomorphisms? If I am calling it homomorphisms, then it has to preserve finite meets and arbitrary joins. Example is obviously examples of frames include, yes, OX for topological space X, spaces X. But this is not the end of the story. Now, normally, if you think about, however, O is not a functor from top to frame. Can you tell me why? Functions reverse the direction, right? So therefore, O from this to frame op is a functor, because inverse image of open is open. Yeah, so F maps to F inverse. So for this reason, actually, there is another definition where we call the frame a locale. So define a locale to be a frame, but a locale homomorphism to be the dual of a frame homomorphism. So, i.e., what I am saying is the category of locales is the dual category of the category of frames.
So does that L need to be a set?
L is a set, obviously, it's a lattice. It's a lattice, so therefore it is a set. No, we don't want to extend anything. Frame is just the category of lattices of these are models of this infinitary theory. Yeah, it has finitary meets, arbitrary joins, and infinite distributive law. So then O is a functor from top to lock. It's a covariant functor. Yeah. And well, with respect to regular topology, yeah, open cover topology, let me call it JReg. So what happens is that you can recover your original OX. I just want to give you some interesting bit. It's a remark or a note that if I work in the category of sheaves over X, and I take this terminal object in that category, that will return OX. More generally, okay, so the subobjects of the terminal object again in the category of sheaves over L. I mean, maybe I should define now. So sheaves over L comma J reg. Regular topology can also be defined on a locale, and it will recover L. So there is a way of recovering the subobject lattice of the terminal object. It's called a subterminal lattice. So subterminal lattice will return our original topology.
What would we view the locale as a category as a poset?
Locale as a category, as a poset, yes, yes. It has got all limits and all co-limits. Once it has, once it is a complete lattice, then it is automatically like complete semi-lattice, then it is automatically a complete lattice. If you have finite meets, then you can define arbitrary meets. Arbitrary meet of a subset is the join of all the common upper bounds, which is defined.
So, like in vague sense, like if
Huh?
I want to visualize the last one, the more general.
Mm-hmm.
So, for the lattices, we had, let's say, the points, and we are actually retrieving it from the morphisms that we had in between those points. Is that like that? Like, I mean, because when we are
With respect to inclusion, Uh-huh.
automatically the Yoneda will actually come.
Yoneda is not relevant here.
So
No. See, this is what, like, the sublattice. I mean, the lattice of subobjects for terminal, that will be like one is like one everywhere. And then you have to decide where should be ones and where should be zeros. That will give you subobjects of the terminal object. And that will recover this. I'm not claiming that the category of pre-sheaves on L will give me L back. But what I'm saying that for a locale, the category of sheaves on this, like, by the way, I haven't defined this object so far, the category of sheaves on a site, but I will define it soon. But this is just a remark. Yeah, so you can recover some of this original structure. You obviously cannot recover the points of the topological space. Yeah, that's too much to ask for. But you can at least recover the lattice structure of open sets. Okay. Third example. Given a poset P less equal, you can think of a poset as a category. Define the dense topology on P. Yeah, so this is J dense. So what is the property that if P is in P, say that D subset of all the lower bounds of P is dense below P, like this is the definition, dense below P, little p, if for all R less equal P, there is some Q less equal R such that Q belongs to D. Does anybody recognize this? Yes, in forcing, you precisely use this topology. So set theory motivated this example. Okay, so define J of P, J of little p, to be the collection of all D's such that D is subset, such that for all Q in D, Q is less equal P, and D is dense. D is a sieve dense below P. A sieve in a poset is nothing but a downset. Okay, so it's a sieve which is dense below P. So that is the collection. So with respect to that, like this is J dense actually. If you want, you can write J dense.
These are like open dense.
No, don't think about openness now. Yeah, these are just the covering sets. So the sheaves with respect to this will give you J dense sheaves, or it will help you to construct other models of the theory of, like the Zermelo-Frankel set theory. So Paul Cohen actually used this particular topology, yeah, for proving that axiom of choice and continuum hypothesis are independent from the rest of the axioms of Zermelo-Frankel set theory. More generally, like the story doesn't end here, more generally, given any small category C, say that, well, I'm not just, S belongs to J dense C, where C is an object, if and only if for all f from D to C, there exists some G from E to D such that f composed with G is in S. So this is the definition. I mean, I'm writing if and only if, but I should write it as a definition. This is the definition of J-dense on any category C. Okay. Finally, atomic topology. Okay. Atomic topology, yeah, I mean, this is the dense topology again here. Atomic topology has something to do with weak pullbacks. So assume that in C, any bold diagram, any solid diagram can be completed to a dotted diagram. What is the solid diagram? Like I'm given any arrow, any pair of arrows. So what I'm asking is that we should be able to complete it to a pullback like diagram. There is a commutative square. Okay, if this weak condition is satisfied, I mean this condition will always be satisfied.
Any pair of morphisms has pullback.
No, I'm not saying it's universal. I'm just asking that there is a diagram which makes it complete.
So, like any complete category would satisfy this diagram at least? Because you can just take the
Initial object. If it has an initial object, then it will satisfy this. Yeah, because
even if it is complete then,
yeah, if it is complete, then obviously it satisfies. But usually you don't ask for any nice conditions on category C. C of sets is already nice. It's complete, co-complete. It has sub-object classifier. Everything happens. So define the atomic topology. So say that S belongs to J atomic of C if S is non-empty. All the non-empty sieves are taken, like everything is covering. So the localization with respect to this is going to be really very small. Yeah, you are trying to make the smallest possible thing. It may or may not exist. It only exists if this condition is satisfied. Okay, now once we have seen some examples, let me go back to the motivating example, like a pre-sheaf is a sheaf if there is an equalizer diagram. Now we have to describe a similar condition for a sheaf on a site. Sheaves on a site, okay? So if P is a pre-sheaf and S is a covering sieve, then a matching family for S of elements of P is a function that assigns to each f from D to C in S an element xf in PD. Okay, so it's an assignment from the morphisms in S to elements in respective domains. So it's like a choice function. Yeah, you are taking F and then you are mapping it to an element XF in P domain F. It's a choice function. Okay, so the matching family, if this matching family has a unique amalgamation where S is not fixed, S is any covering sieve, then we would have said that it's a sheaf. So try to compare it with the existing notion that you know. What is a covering family? It's an open cover. So D, the elements D, what are they going to be in the open cover? The individual UIs. So you want to assign an individual section X sub I in P of UI. Well, that's precisely what we did, right? And such that, of course, such that the condition is there that PG applied on XF is equal to XGF. XFG, I suppose. Yes. XFG for each G from E to D. Because we have to talk about a sieve. Sieve is a right ideal, so it has to be closed under precomposition. So the collection of elements should satisfy this. Well, what does this say? PGXF is equal to XFG. In the case of open cover topology, it says that you take a section on UI and you go to something smaller. Let's say that smaller thing is UI intersection UJ. Yeah, then the element that we have chosen is actually a restriction of this. That's precisely this condition. It's actually the sheaf. We are trying to reproduce the sheaf condition. Yes. So, an amalgamation for the matching family is some X in PC such that PF of X is equal to XF for each F in S. Okay, so now what is the definition? Yes, so say P in C hat is a J sheaf if every matching family, if every matching J family has a unique amalgamation. Okay, so that's, you can, I hope you are convinced that it's the same definition. Okay, equivalently, I can express it in a slightly different way. So, equivalently, recall that each sieve, each sieve is what? It's a subfunctor. Equivalently, P is injective with respect to the inclusion S to YC for each J covering sieve. S. Okay, what I mean is this, that for all maps, for all blue maps to P, there exists, like it's strongly injective, there exists a unique extension. I mean, I should say strongly. There exists a unique extension to IC. Yeah, you remember in projective objects, we saw that lifts exist. Lifts with respect to epimorphisms. Injective is dual. Yeah, so this is a strong strong injectivity property.
How is the blue arrow from S to P, how does it correspond to a matching family?
Yes, that is a matching family. You can verify that. A matching family is just this, okay? So equivalently, now I am also going to give you one more condition. Okay, so PC, then this is E, then there is product of P of domains of F, F in S, and then there are two maps, yeah, where I am taking product of P of domain of G, where F and G are morphisms, then F is a morphism in S and G is a morphism such that G composed with F is in S. F composed with G is in S, right? F is applied later. So this happens, and then there are two maps, like this is little p, this is little q, and is an equalizer diagram. You tell me what the maps are supposed to be. This x here is supposed to be taken to PF of x, correct? F in S, and then any family XF over here, where will P take it to? Under P? Huh? PG of XF, okay. XF F in S. Okay, so that's the second one. And this is F composed with G, XFG. And under Q, it will go to PG of XF. So this is an equalizer diagram. So it's exactly identical to that. Yeah, so this is the definition finally. A Grothendieck topos E is any category equivalent to the category of sheaves on some small site. This is actually the definition of a Grothendieck topos. Any category equivalent to the category of sheaves on a small site. Some properties that obviously there is a localization functor. This, so you take pre-sheaves C hat and sheaf Cj. This is a reflection, obviously. Reflection means the inclusion has a left adjoint. There is a localization where A is called the sheafification functor. And is left exact. Left exact means it also preserves, left adjoints normally preserve co-limits, but here we are asking that it preserves finite limits as well. Okay. And finally, an analog of the Gabriel-Popescu theorem, and that is the Giroux theorem. So it will give you the conditions like, so Giroux was a theorem, was a student of Grothendieck. So this theorem says like this is analog of Gabriel-Popescu. You remember Gabriel-Popescu, it says that every Grothendieck category is a localization of module category. Now, module category here is replaced by C hat, pre-Schiff category. So it's a localization. Yeah, that's the definition. So how was the Grothendieck category defined? It was an abelian category which had some more conditions, arbitrary small co-products, then the direct limit of short exact sequences is again short exact, and it has a generator. So now it's going to give you the other side. So Giroux theorem, it says that a category E is a Grothendieck topos if and only if it is a locally small Cartesian category such that the first condition is small disjoint coproducts exist. Disjoint coproducts means what? That whenever you take two different objects, then their intersection has to be 0 in the subobject lattice of the coproduct. Small disjoint coproducts exist and are stable under pullbacks. Then each epi is regular. Do you remember its analog in the abelian world? Each epimorphism is normal, it's a co-kernel, right? Then every equivalence relation is a pair like this, sorry, E to R. Oh no, this is correct. E is a kernel pair and has a co-equalizer. Fourth condition, so this is like has a kernel pair, is a kernel pair and has a co-equalizer. This is analog of every monomorphism is normal, is a kernel and has a co-kernel. Okay, the fourth condition is about short exact sequences. So every exact fork means something like this. So the morphism from E to Q is a co-kernel of this pair of morphisms, and the morphisms from R to E, they form the kernel pair. Huh? Co-equalizer, yeah, co-equalizer for this pair, and this pair is the kernel pair of the other morphism. So this is like a short exact sequence. So is stable is stable under pullbacks. And finally has a generator. So it's exactly like Grothendieck's axiom for Grothendieck categories. Okay, so this is like the property 2, 3 and 4, they together say that it's an abelian, like the appropriate analog of abelian category. And property 1 is analog of AB4 and AB5, and property 5 has a generator, same thing. Any questions? So this is Topos theory. It's very niche topic, you can say. Very few people in the world properly know it. If you are interested, you should study more. Yeah? And this is the end of our final lecture. Any questions? If not, yeah.
That topology thing, it looks more like a neighborhood filter.
It's a neighborhood filter. Yes, you can also look at it from a different perspective. Yes, neighborhood filter. Okay, so let's end the lecture here. So this is our, these are our in-class participants for the physical course. So I thank all of them for making this course interesting, and I also thank all the online participants. And here are the cameramen, without whose efforts this wouldn't have been possible. Thank you all.